believe where we finished yesterday was these two here. Yes? Yeah, we finished EDFH. Yeah, all 15 of them. Bounded and unbounded intervals. There's two main intervals that we have, bounded and unbounded. Bounded is going to have two endpoints. Unbounded is going to have one endpoint and go on in one direction forever, to infinity. And the pun is, and I've avoided saying this punny joke all day, because unbounded go in one direction, unlike one direction. But bounded has two endpoints, unbounded has one. Now, bounded intervals. Now, let's look at that first sentence here. Let A and B be two real numbers such that A is less than B. All that's saying is that A and B, we have two real numbers. Doesn't matter what they are, they're real numbers. Okay? And A is less than B. So whatever A is, doesn't matter what A is a real number. We could say it's 14. B has to be bigger. It could be 15, it could be 16, it just has to be bigger than it. And we use this A and B so that I can define any bounded interval. Any 2 points where one's to the left, the other's to the right. And that's really all it's saying. We have 2 points, one's to the left, one's to the right, and it's going to be everything in between. Because then A and B are the endpoints of 4 different bounded intervals that we could have. We use these letters to define any situation that we could possibly have. Now, out of these 4 possibilities, the first inequality expression of this here is that A is less than or equal to X is less than or equal to B. As an interval, we're going to say bracket A, comma, bracket B. Brackets are around both. Because we're saying that both endpoints are included, giving us this here. The next one is that neither of the endpoints are included. So A is less than X is less than B. Interval notation, we would put parentheses because parentheses are not included, brackets are. The next one we have, A is less than or equal to X is less than B. So we're saying that A is included and B is not. And lastly, the last statement is kind of similar to the one before it. This time A is less than X is less than or equal to B. So we either have that both endpoints are included, neither endpoint is included, or one endpoint is included and the other is not. So really the third and fourth are almost the same thing. It's just changing which endpoint is included and which one isn't. Interval notation. We do not have a variable. We're just talking about the endpoints. Which endpoints are included, which ones aren't. We good with this here? We've seen this before, yes? The other type of inequalities that we can have are unbounded. Let A be a real number. Each interval on the real number line shown below is called unbounded. We have a point, a number, and it's going to go either to the left or to the right. Now our first one, we're saying that X is less than or equal to A. Since it is less than or equal to, we have a bracket with A. And since we're saying greater than, it's going to go to infinity. Infinity will always have a parenthesis. Because no matter how hard we try, we can never get to infinity. Infinity is not a number. It is an actual concept. So infinity is not a defined number. It is a concept. The next one we have X is greater than A. The infinity still has the parentheses. Our A now also has a parentheses because we're saying it's not equal to it. Our next one, X is less than or equal to A. Now we're going to negative infinity. We're saying it's smaller. Smaller numbers always on the left, bigger numbers on the right. Even though negative infinity is not an actual number, we still treat it like one. Last one we have, X is less than A. So negative infinity, comma A, both have parentheses. The last one we have really doesn't have a single statement, but I do consider it unbounded, but we're just going in both directions. It's all real numbers. It's everything. Questions on this here? We good with this here? Sweet. Now, at this point here, we'll talk about kind of infinity, and part of the reason we use parentheses with it. Infinite hotel. And this is kind of stating why we have parentheses, because again, some infinities are bigger than others. Why we can never actually get to infinity. And the best kind of thought experiment with this, or kind of explaining this, is one that's called the infinite hotel. Okay? Now we call it the infinite hotel because there's an infinite number of rooms in this hotel. I will be the receptionist, I will be the clerk, kind of helping people get checked in, getting rooms. Now at this hotel, we have infinite rooms, and every single room is full. There is someone in every room, even though there are infinite rooms, they're all full. And a customer comes in asking for a room. And we want to be hospitable and try to make accommodations so that we can give them a room for the night. And I come up with this idea. We ask the person in room 1. So they're in room 1. I ask them to move to room 2. Okay, the person in room 2, we ask to move to room 3. The person in room 3 is moving to room 4. The person in room 4 is now moved to room 5, 5 to 6, 6 to 7, 7 to 8. There are infinite number of numbers, infinite number of rooms. We move everybody down 1, which means room number 1 is now open, yes? So the new person moves into room 1, but that also means our infinite hotel just got 1 room bigger, yes? This is, again, why we cannot get to infinity, why we can't put that bracket there, because it is not going to be included. Even if we tried, there is always going to be some infinity that's going to be bigger. We're ready to take it a step further. Well, the entrepreneurial that the CDO of the Infinite Hotel is built a second Infinite Hotel. And it is beyond me why he built it across the street, but he built it across the street. So we have 2 infinite hotels right across the street from each other. Surprisingly enough, both of them are full. They both have infinite number of rooms, and every room is full. But tragedy has struck, and Infinite Hotel B burned down. But luckily, everybody in Infinite Hotel B made it out perfectly fine. No one was hurt. But they do need a hotel room for the night. They already paid, so we need to be accommodating and giving them their room that they paid for. So we got to figure out how to fit everybody from Infinite Hotel B into Hotel A. Well, we're going to do something similar. Not exactly the same, but we're going to ask the people in Hotel A, so the person in room 1, to move to room 2. However, we're going to ask the person in room 2 not to move to room 3, but we're going to move them to room 4. We're going to ask the person in room 3 to move to room, y'all know? Not quite. Well, there's one before. 6. Person in room 4 would move to room 8. Person in room 5 would move to room 10. We're moving each person to the next even number. How many even numbers do we have? Infinite. There's an infinite number of even numbers, yes? Which means all the odd numbers are now open. And how many odd numbers do we have? So that means we can move Infinite Hotel B into all the odd numbered rooms in Hotel A. We just made infinity twice as big. We're starting to see how we can never actually get there and why it's a concept. We call it a concept, not an actual number. It is actually possible to move 7 infinite hotels into a single hotel. The math starts getting a little complicated as we get there, but it is possible to do this. Crazy to think, but it is possible to do. And again, we'll not talk about this pretty much after this, but it is an interesting thought experiment to just think about how we can manipulate infinity this way. Now, the next thing we're going to actually do, and actually shows up on homework, because unlike infinite hotel, that's not going to show up, is interval notation. So we want to write -2 is less than or equal to x is less than or equal to 3 as an interval in interval notation. Now, you do not have to graph it. I am going to graph it because for some students, seeing it graphically can help us get to the interval. If you don't need to see it graphically, if it doesn't help, you don't have to do it. Okay? Now, if we're talking about the graph of this here, we have 2 key numbers, the 2 endpoints, -2 and 3. Yes? Now, some teachers and some will say that we do need the 0, we need to keep it scaled, so on and so forth. No, this is as much as I need. We need to make sure that the smaller numbers are indeed on the left, the bigger numbers are on the right. Okay? We have it set up that way. Now, 2, we do have a circle at 2. Now, the question was, will it be opened or closed? Is it included or is it not? So let's look at it. Because we say -2 is less than or equals, yes? Equals means that it is included, so we have to fill it in. Our other spot is 3. Is it included? Yeah, because again, we have equals, don't we? So that means it's included, which means it also has to be filled in. Now we need to figure out where we shade, yes? The way that I remember this for the most part, x is in the middle between our 2 endpoints, yes? So we shade in the middle, it's between them. Now here we have one inequality, we have one statement, we have 2 endpoints, it is bounded. So our interval notation, we'd have our 2 endpoints, -2 and 3. They are a part of the same statement. We're saying it's between those 2. -2 is included. Since it's included, we would put a bracket. Brackets mean included, parentheses mean that they're not. The 3 would also have a bracket. That's all it's looking for. So if having the graph of the number line helps, use the graph. If it doesn't, if you're perfectly fine going from the inequality to our interval notation, do that. We're ready to look at B. So again, I'm going to do a number line. How many endpoints do we have? 1, and that is -1. And again, if I'm going to graph it, I'm just going to graph that one spot because we're either going to shade to the left or to the right. It's unbounded. Now, before we start shading, is the one circle open or closed? Open, because it's not equal to. Now, do we shade to the left or to the right? Left, because it's telling us what? X is bigger or smaller than -1? It's bigger, so we shade to the right. Yeah, because it is indeed bigger. Questions on how we graphed it. Now, interval notation. Our one main endpoint is -1. Now, since it is unbounded, it means we're going to where? So it will have a parentheses with it, but we're going to infinity because we went all the way to the arrow, so we're going to infinity or negative infinity. Here we're going to infinity. Now the negative one would indeed have a parentheses next to it because it's not included. How about infinity? Would it have a parentheses or a bracket? Parentheses, because negative infinity and positive infinity will always have a parentheses next to it. We can never get there. Questions on B? We feel good with A and B? We ready to look at C and D? So C, we have two endpoints, yes? And they are? Negative 3 and 4. Now they are connected together, so they will be in the same interval. The only time they wouldn't be is if we had two intervals in the or statement going in opposite directions, then we'd have two separate statements. The negative 3, is it included or not? It's included, so we put a bracket. The 4, parenthesis. Since it's not included, that spot's open, it puts a parenthesis. Brackets are included, parentheses are not. Questions on this here? The last one, D, on this here. How many endpoints do we have? One. We have 3, yes? Rewrite that 3. 3. Wrote the exact same thing. So that means we're going, especially since we see, especially on the graph, that it hits one of the arrows, we're going to infinity or negative infinity. Which one are we going to? Negative infinity. Negative infinity is not included. The 3, is it included or not? So we would put a bracket. With interval notation, bigger number is always on the right, smaller number is always on the left. Anybody have trouble writing the infinity symbol? Yes? Do you know an easy way to do it? Turn your page and then make an 8. You can rotate your page and then just draw an 8. It's like an 8 that fell down. There's also the funny joke. Do you know what the 0 said to the 8? Nice belt. All right. Since we feel good with intervals, bounded, unbounded, we're going to look at set builder notation. Set builder notation uses symbols to define a set in terms of the properties of the set, the members of the set. It gives us a nice way to write sets that are not nice to write. And what I mean by that is the set of numbers, set of whole numbers less than 10. That was nice to write. Because 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. I can write those nicely. An example I gave yesterday, writing out all of the high school graduates for Concord. That's not nice to write because there's so many of them. Actually writing all of them out is not feasible, and just especially by hand. Just you wouldn't want to do that. You would set a program to do that. So set builder notation gives us a way to do this, to describe the set without having to list everything out. Now there's 3 main parts. We have brace, triangle, bar, circle, brace. Now we're not going to write a triangle and circle. I put those in there to know that we're going to fill something in for those spots. Now the triangle describes the group. What type of numbers are we talking about? Are we talking about real numbers, natural numbers, whole numbers, integers, rational? Don't normally do irrational. Complex numbers. What type of numbers are going to go in this spot? What type of numbers are we describing the set as? Okay? The bar is such that. The bar is such that. And our circle is our description. What kind of numbers are we talking about? Okay. So I'm going to write an example of it next to it. For the most part, if we're talking about real numbers, we're going to write it this way. Brace x bar. Brace x bar. Now, this is going to seem like a tangent, but I've said before, I said it yesterday, mathematicians are lazy. Yes? If we can write it simpler, we can write it easier. We're going to write it that way. Brace x bar. How we read this and what that's saying, that brace x bar is saying the set of all real numbers x such that. So we use three symbols, yes? To say the set of all real numbers x such that. I turned 9 words into 3 symbols. Like I said, mathematicians are lazy. Not in a bad way, but if we can write something simpler, we're going to write something simpler. Such that, now we're going to give a description. I'm going to say that x is greater than or equal to 0. So we've said the set of all real numbers x such that x is greater than or equal to 0. Numbers x such that x is greater than or equal to 0. We turn 17 words into 1, 2, 3, 4, 5, 6, 7 symbols. Condense it down. Now, also listing this out like we did with the whole numbers and our positive even numbers. If we tried to list this out, 0 would be the first number, because that is true, yes? This is pretty much as we're going to write, because what's the next real number after 0? Well, 1 would be, yes? How about 0.1? Would that be after 0? Because that's a real number, isn't it? How about 0.11? How about 0.184721? How about 1.9876543? Is it possible to write all these numbers? Because there's so many that we could write, yes? Another list that we could have is, say, you don't have to write this because it's about to get very tedious. Because we could say 1/2, yes? I could also say 1/3, 1/4, 1/5 are all included in there, yes? Because all of those are between, well, we're just at this point only being between 0 and 1. We could also say 2/3. 2/4 would reduce. So we wouldn't necessarily list it because it's already listed once. So we can say 2/5, 2/7, 2/9, 2/10. Now the reason I'm doing odd numbers is because all the evens would reduce down to a previous one. But we can say that's true, yes? But we could also do it with 3s, 3/4, 3/5, 3/7, anything that doesn't reduce by 3. We can also do it with 4 on top, 5 on top, 6 on top. That's a lot of numbers, isn't it? Doesn't that mean also that I can fit an infinite number of numbers between 0 and 1? So is it feasible to actually list this out like we did all the whole numbers less than 10? No, this is not feasible. We can't actually list it all out. That's why graphically or set builder notation is nice. It gives us a way to define these numbers and describe these numbers without listing every member of the set. Now our positive even numbers, we can set a pattern. Here, there is no pattern we can set to define all this, because we'd have to list every single one of those out. That's taking way too long. That's why this is nice. Okay? Now, we're going to look at these set builder notations and kind of describe these here. So the first one, brace x bar, the set of all real numbers x, such that x is less than a. What is a? A is a number, yes? So graphically, we'd have a point A as a point on this number line. If it's somewhere on the number line, it could be any number on the number line. But what we're saying is that x is less than it, yes? So would the point, our circle at A, be opened or closed? Would we shade to the left or to the right? Mm-hmm. That's it. That's all it's saying. We good with that one there. Let's look at the next one, the set of all real numbers x. So x can be any real number, because it's in that group of real numbers, such that x is not equal to 3. So it did give us one number. Let's go and put it on the line. With a circle. Would this circle be filled in or left open? Left open because we're saying x is not 3, yes? But what can x be? So what can it be? We could have it be infinity. We could also have it be what? 4. We could have it be 6, 7, pi, as long as it's not what? 3. It can't be 3. It's any number but 3. So how would we graph this? We would shade to the left and to the right, because it can be anything but 3. I don't know what 3 did to this problem, but it's not included. Let's look at the next one, the set of all real numbers x such that negative 4 is less than x is less than or equal to 6. How many endpoints do we have? 2. We have negative 4 and 6. At negative 4, since negative 4 is smaller than 6, it would be to the left, 6 would be to the right. Negative 4, is it opened or closed? It's open because it is not equal to it. 6 would be closed. Now, where are we shading? In the middle, because x is in the middle, we shade in the middle because we're saying negative 4 is less than x is less than or equal to 6. So the values of x are bigger than negative 4 and smaller than or equal to 6. Everything in between, and we're including 6. Questions on this here? So you're saying what to the next one? That this E symbol in mathematics and how it's being used is element. X is an element of a given number set. So we could put, I've been using the same number. You know what, I'm going to change it up. No, we're going to use the same one. Our integers. We can say x is an element of the integers such that x is greater than or equal to negative 9. So when we're talking about a group that's not the real numbers, if we wanted to, I'm going to put it back, but if we wanted to, I could say x is an element of the real numbers such that this here, it is redundant. Because I don't have to put it at all. Because if it's not there, we just have brace x bar. It is the set of all real numbers x such that it already describes it. If we're using this E, we're going to fill something in, such as the integers, our rational, our whole numbers, our natural numbers. We don't normally do irrational. We can put the I there. Don't normally. So we're saying x is an element of the integer such that x is greater than or equal to negative 9. So we would have negative 9 and we'd fill it in, yes? I'm going to go and put negative 8 next because it is included. It'd be a negative. It would be an integer that's greater than negative 9, yes? Would we shade between negative 9 and negative 8? Because what's a number between negative 9 and negative 8? Huh? Negative 8.5. Yeah. Is negative 8.5 an integer? No, because negative 8.5 would be a rational number. It would be a fractional number. Yes? Negative 8.5 is not an integer, so we can't shade it in. So even if we did have it, say, let's expand it out. Say it was the rational numbers. We still couldn't technically, we would, but we can't technically shade in between negative 9 and negative 8. There are irrational numbers that exist between negative 9 and negative 8. Y'all are seeing how this can be tedious to try to graph this? Because that means the next number would be what? Negative 7, negative 6, negative 5. We don't have all of it. It's just those set points. We'd just be putting dots at every single one, and that's going to continue us on indefinitely. We're definitely not going to graph the last one. The set of all real numbers x such that x is even. 0, 2, 4, 8, 10, 12. We'd just be hitting those points. I'm not going to worry about graphing that because, again, that's less of a graph and more of points. But I put it up there so that we can see and think about this here. This making sense? Does it seem like it feels like it should be more than this? Would y'all agree with that statement? It feels like there should be more with the set builder, but this is not really it. It's a way to describe it. Sketch the graph of each set of numbers. So A, the set of all real numbers x such that 2 is less than x is less than or equal to 5. So we have 2 points on this number line, yes? 5 and 2. Are these spots going to be both open, both closed, one open, one closed? 5 is closed, 2 is open. Because the 5 does have the equal to sign, the 2 does not. Now where do we shade? In the middle, because x is in the middle. Now one thing I will say about set builder notation, we cannot use interval notation and set builder notation together. And what I mean by that is we cannot write this as brace x bar, the set of all real numbers x, such that this is not a proper way to write this. We cannot put interval notation into set builder notation. If we're going to set builder, we've got to turn it back into an inequality if they give it to us as an interval. We good with A? Let's look at B. The set of all real numbers x such that x is less than or equal to 0 or x is greater than 4. So we do have 2 points. Yes? 0 and 4. Is one, both, or neither one of these filled in? One. Which one? The 0. Okay, we finished with figuring out which one's open, which one's closed. Now we need to shade. Yep. So since x is less than or equal to 0, we would shade to the left. And since x is greater than 4, we would shade to the right. Now it is very tempting to always shade out for or statements because or means we're going to pick one or the other. One of them has to be true. Or both can be true. Because it's like with English, y'all learned way back when y'all were on the, if you were here, on the other side of the street. Or statements, or, because you can have a hamburger or a hot dog, which means you could have a hamburger, you can have a hot dog, or you could have both, because or is, it does work for both. Now, I'm going to change this just a little bit. Let's pick this. Let's say it had greater than or equal to and less than 4. I'm flipping it. So x is greater than or equal to 0. So for the 0, we would shade to the right. X is less than 4. Now we're shading to the, when I flip those signs, we were shading towards each other. We just shaded the entire number line, yes? Now the question is, and I had this asked earlier, do we still include 4? Because it was open before, yes? So here, let's plug it in. Is 4 less than 4? Is that a true statement? No. Let's look at the other one. Is 4 greater than or equal to 0? Is that a true statement? No. Is 4 bigger than 0? Yeah. So is it true? Oh, yeah. Because or statements, how many of these statements have to be true? Is one of those statements true? Yeah. So now that we switch it, yes, 4 is still included because it made one of them true. So if it is pointing at each other, we just included the whole number line. It is possible. We don't normally set it up so that both are possible. We normally have one side or the other. Let's look at the last one that I have on this here before those other two. For all real numbers x such that x is less than -2 or x is greater than 0. So our two spots are -2 and, 0, yes? 1, both, or neither circles shaded in. 0. None of them. -2, are we going to shade to the left or to the right? To the left. 0, are we shading to the left or to the right? Mm-hmm. Yep. That's it. Questions on this here? Do we feel comfortable with this here? Do we need to see another example of one of these? Do we feel good with these here? Okay. Now, in the note sheet, you do see that there are 2 more examples, yes? I do put a lot of examples in here just to make sure we understand what we're doing. Like I said with the homework, I only assign the ones that I think necessary to master it. That kind of goes the same thing with the notes. If, again, I check in and we feel that we're good with this, we don't need to see another example, I'm not going to do another example. Because at that point, if we understand it at this point, doing 2 more ain't going to make it clearer. Because at that point, we say we're good. We move on to the next piece, the next type of problem. Sound good? So just because the packet's massively or thick, either A, we're going to blow through it, or B, there might be some of them we're not going to hit because y'all feel comfortable with it. Well,